Well, that's a voice. All right, so sorry I don't have video today. As some of you guys may know, my router seems to be broken. So that means that I don't really have the data. I'm using my wife's phone to tether. I don't really have the data to broadcast both video and screen share. So we're just going to do screen share and we will get started. So we talked last time at the end of last lecture, we talked about, I introduced this idea of magnetism and how you can produce some sort of, so I can't connect Ethernet to this tablet. We talked about how you can produce some mysterious force between two lines of charge and, two wires with current in them, my bad. And that is this mysterious force. And it turns out if you have a moving charge near those wires, that moving charge will also produce or will also experience a force. So and that force is the magnetic force. And so what we're going to do is we're going to assume that there is some magnetic field, and we're going to try to understand, given some external magnetic field, how charged particles experience a force. So let's just jump right in. So given some magnetic field B, and remember the magnetic field, we use the letter B for the magnetic field. I actually don't really know why. I think it's a historical thing from the 1800s. But given that magnetic field B, and it's just like an electric field, it has a vector at every point in space, we can experimentally determine the following results about how the force is related to various quantities. So the first is just like the electric field, or just like the electric force. So we know that the magnetic force depends on charge. So if you have a charged particle moving, then that charged particle will experience a force. So there should be a relationship between how much charge the particle has and the force it experiences. And indeed, we find experimentally that the magnetic force on a charged particle is proportional to the charge, the magnitude of the charge of the particle. So if you have a charge that experiences some magnetic force of say 5 newtons, and then you double that charge, it will experience a force of 10 newtons. Here, by the way, Q, this is it's the charge of the particle experiencing the force. So far, this is just like the electric force. The bigger the charge, the bigger the electric force. Another factor is that the magnitude of the magnetic force that's felt is also proportional to the magnitude of the magnetic field. Again, just like the electric force, if the electric field is twice as strong, you get twice as much electric force. Nothing surprising here. And in fact, it kind of had to be this way because that's kind of how we define force fields. We define force fields like the electric field and the magnetic field to have the property that the resulting force is proportional to the field. So that's fine. Now, we also mentioned last time that if you just put a charged particle that's stationary near these wires with current running through them, the charged particle won't move. And so that's how we determined that the force requires motion of charges. And indeed, the force that the moving charge feels is actually directly proportional to also, and again, you can verify this experimentally, it's directly proportional to the magnitude of the speed or the magnitude of the velocity of the charged particle. So here is the velocity of the particle experiencing the force. So if it's moving twice as fast, it feels twice as big a force. By the way, we are not at all talking about how magnetic fields are produced yet. So just imagine that there is just some magical or some magnetic field that just exists. The question is what force does that produce on moving charged particles? And all of these properties that we've listed so far are experimentally determinable results. And you could do this experimentally by just taking magnets which produce magnetic fields, and then putting charged particles in there and seeing what happens. Another property, which is strange, the magnitude of the magnetic force is proportional to the sine of theta, where theta is the angle between the vector v and the vector b at whatever point you're evaluating at. Now that's strange. This is new, and it, like, there's no equivalent relationship for the electric field. And so what we find is that if the magnetic field points in the same direction as the velocity vector, you get no force. And if the magnetic field is perpendicular to the velocity vector, i.e. theta is 90 degrees, then you get a lot of force. Yeah, you know what? Actually, I can use a different audio if it's annoying. Yeah, let me connect a different audio, because it's 100% the pen. There. Is the audio better? And now you can't hear the pen, hopefully. Okay. Right. So I'm just using the camera audio, but I'm not using the camera video. Right. So the point I was making is that the if the vector, the velocity vector, is perpendicular to the magnetic field at whatever point the particle is at, then the force is maximal. So it's only when the velocity is perpendicular to the velocity vector that you actually get any force at all. And just towards products. The last result, which you can again experimentally determine just by putting a charged particle in a magnetic field, is that the force on the charged particle is proportional to it's perpendicular to two things. It's perpendicular to the magnetic field, and it's also perpendicular to the velocity. And so this is also weird, because for the electric field, we saw that the force was in the same direction as the electric field. Here, we're seeing that the force is perpendicular to the magnetic field, but it's also perpendicular to the direction of motion. Now, as Joseph guessed, this is precisely what you would get if you formed a cross product between the velocity vector and the magnetic field. And then we would need to incorporate that the charge is included. So the end result of putting all of these relationships together, all of these proportionalities, is that the force on a charged particle in a magnetic field is Q times the velocity vector crossed with the magnetic field. So that is the magnetic force. You'll find that this formula follows all of the 5 things that I just outlined. If you double the charge, you double the force. If you double the magnetic field, you double the force. If you double the velocity, you double the force. If you the magnitude is related to the sine of the angle, which is involved with cross products, and the force is perpendicular, which is also a result of cross products. So if I were to just draw a quick diagram, let's say that blue is I actually really don't like blue for the magnetic field. Let's use like a purplish red. I guess that's purple. So purplish red, or purple, is the magnetic field. If we have a charged particle, blue, that's moving with some velocity, say in this direction, this is the magnetic field, then the question is what force, and let's say it has positive charge Q. Let's give it plus Q. Then the force would be, well, we'd have to do the cross product. That's Q. It doesn't matter. Because you can always multiply a vector by a scalar. Then we can use the right-hand rule here. Oh, God, this is the one class where not having a video sucks. Maybe I'll actually try with the video, and if it's really slow, call me out and I'll disconnect it. Because I'm gonna need to show you my right-hand rule. So I have to use my left hand because it'll look like my right hand to you, but I'm using my left hand, but that's just for your purposes. So we would take our cross product, and so we would do V, which points in that direction. We'd curl it in the B direction, which is this way, which tells you that the force points into the paper. So I'm using the left hand because from your perspective, this is my right hand. If I use my right hand, it looks like my left hand for you guys. And if I did the right hand rule here, it would appear that it's pointing out of the page, whereas really it should be pointing into the page. That's why I have to use the left hand. I had to do it last quarter too. It's annoying, but it's what needs to be done. Anyway, yeah, I haven't mirrored the camera, so that's why it's like that. I suppose so I'm gonna do it that way because if I mirror it, then it'll look confusing to me. Anyway, right, so the force should point directly into the piece of into the screen. You guys can try with your right hand rule that the force should point into the screen. And so the force is going to point this way. Right, so hand goes in the direction of the velocity vector, curl it in the direction of the magnetic field, which is to the right, and then your thumb will point in the direction of the force. Now, you have to view it from your perspective. My thumb is pointing into the screen for you guys, right? So the force is into the screen. And if I were to do this in real life with, I'm not going to do that because that'll confuse you. But anyway, that's what it'll look like. So it'll point into the screen. Right, and so by the way, just as a quick note here, this symbol, circle with an X in it, that will be used a lot to indicate a vector that's pointing into the screen. And the way to think about this, oh, and let me give one more. A circle with a dot in it is a vector pointing out of the screen. It is weird, but it's super useful. And by the way to think about these is just imagine that there was like a physical arrow from like a bow and arrow that's either pointing into or out of the screen. If it was pointing into the screen, you would just see the tail feathers, and so it looks like an X, and then we put a circle around it. If it was pointing out of the screen, you just see the tip, so we put a little dot with a circle around it. That's where those come from. Right. So that's the direction of the force vector. It points into the screen here, which is kind of weird. Now, just as an aside, we should talk about units. So the units of the magnetic field, B, well, we know it should be force divided by charge times velocity, right? Because we can just establish that from this equation. So the units should be force divided by charge times velocity, which is just newtons per meter per second coulomb. And so this can be rewritten. Remember that a coulomb, 1 ampere is a coulomb per second. This is a newton per amp meter. And this is given the name Tesla, not the Elon Musk variety, but the Nikola variety. It has the name Tesla, capital T. And so just as a quick aside, the electric fields that we work with in like real life, an electric field strength of like 1 volt per meter, which is the appropriate units for electric fields, that would be like the base SI unit. That's like relatively normal. That just means that you have a 1 voltage difference across 1 meter. And 1 voltage isn't that hard to get, or 1 volt isn't that hard to get. And then to put a 1 voltage distance across 1 meter, not very big. So it's like kind of a reasonable value. But if you go and look at the magnetic field that is required if you want to have 1 Tesla worth of magnetic field, that's a lot. Like the magnetic field from the Earth, and the Earth is a huge magnet. The magnetic field from the Earth near the surface of the Earth is something around 30 microtesla. So 1 Tesla is a huge magnetic field, and that's why it can like rip watches off. Like for example, MRI machines have very large magnetic fields on the order of 1 or 2 Tesla, and they can like pull metal off of you and pull metal out of you if you have metal in you. So large magnetic fields are of the order 1 Tesla or more. Smaller magnetic fields like fridge magnets are going to be smaller. There's another unit that's relatively useful that people use instead of Tesla because Teslas are very big. This is the Gauss. So 10,000 Gauss is 1 Tesla. So which is to say 1 Gauss is 10 to the minus 4 Tesla. It's just a separate unit. It would be like saying it's like a centimeter, but it's a Gauss. It's just a different name. And it's named after the same guy as Gauss's law. Right. So there's nothing in principle stopping a charged particle from experiencing the electric force and the magnetic force at the same time, right? You can have an electric field and a magnetic field. Like if you have a magnet and you have some charges that are separated to produce an electric field, you just get both. Like they can both exist at the same time. So if a charged particle is in both, an electric field and magnetic field at the same time, then it'll experience a more complicated force. But it's really not that complicated. It's just the sum of the electric force and the magnetic force. Sorry, there shouldn't be a Q there. So the sum of those two forces, you have QE from the electric force, you have QV cross B from the magnetic force, and the resulting force is just what happens if you have both. And this formula has a name. It's called the Lorentz force. So when people talk about the Lorentz force, this is what they're talking about. They're talking about the force that's due to electric and magnetic fields. Right. So let's dive a little bit deeper now into what happens if you put a charge in a magnetic field. Is the connection okay, by the way? Just want to get a good feel, like the video's all right. Okay, that's good. So let's say that we set a charge in motion perpendicular to a magnetic field. The question then is, no, that's a V, sorry. V cross. The question is how does the magnetic field influence the motion of the charged particle? Like, will it experience sinusoidal motion, or what happens? Because it's not quite as easy as it just moves in the direction of the magnetic field, right? The force is perpendicular to the magnetic field and perpendicular to the velocity. So it's a little bit more complicated. So let's put a charge in motion. And it has to be perpendicular to the magnetic field, because if it wasn't, then it wouldn't experience any force. Set a charge in motion perpendicular to a magnetic field. So, and let's just figure out what happens. So first, because the magnetic force is perpendicular to the velocity vector, we have to have that the force vector does no work. And the reason for that is that, remember that the work is just force times the path length, or times the path, like the path vector, or a small amount of work is force times the path vector. And the path vector is in the same direction as the velocity. So if you have a particle traveling like along this path, then the velocity vector at this point points this way, and the velocity vector at this point points this way. But because the force is always perpendicular to the velocity, the force never points in the direction of the path vector. The force is always perpendicular to the path vector. And so what you would have is that the dot product between the force vector and the path vector vanishes. And so you can have no work. Like there's a general rule, and this only applies for charged particles in a constant magnetic field. But the general rule is that the magnetic field does no work. And the end result is that if there's no work done, then the kinetic energy stays the same. Because remember that work is how forces change the kinetic energy. W equals delta K, or delta KE, that's the work energy theorem. And so what we have here is that the magnitude of the velocity is constant. And that's because the kinetic energy is proportional to the magnitude squared of the velocity, or the squared magnitude of the velocity. And so if the kinetic energy doesn't change, then the magnitude can't change. Secondly, we have another a little bit of analysis that we can do. Because the force is perpendicular to the velocity, and again, this is just the same thing that I just wrote before, we also get that the acceleration is perpendicular to the velocity. And this might be starting to get familiar. Because the force is constant, and the reason it's constant is because the velocity isn't changing. The magnetic field is constant. I should put constant. It's a constant magnetic field. That's important. And the charge isn't changing. So the magnitude of the force shouldn't change at all. And the velocity will always be perpendicular to the magnetic field. So it will always be, the sign of the angle will always be constant. So the force is constant. We get circular motion. So remember from 9a, circular motion happens whenever you have acceleration that's perpendicular to velocity, and when you have the magnitude of the acceleration is constant. Those are the two required types of motion, or two required features of circular motion. And so if we have a magnetic field that looks something like, let's say it's into the board or into the screen, and it's constant. So all of these are spaced the same distance away. So this is the magnetic field. Remember, this means into the screen. Then if we start a charged particle out, say here, with say, let's put it here. And let's say that it has velocity in this direction, that's perpendicular, right? Let's say it has charge Q and mass M, because charges can have mass. Then the question is what type of motion does it have? So if it's going this way, we've established it should have circular motion. And so it'll go in a circle like this. And the radius is whatever the radius will be. So let's call this R, the radius. It will just move, and it should make sense. So at the instant in time when it is at the bottom, the velocity is to the left. The magnetic field is into the into the screen, and so we can use the right-hand rule. Let me get this right. V cross. There we go. So velocity is left. B is into the screen. So the acceleration points upwards, which would cause the charged particle to turn to the right. And once it's on the left-hand side, the acceleration would be, or the force would be to the right. And so it would turn further to the right, and so on, and it would go in a circle. So the question then is, how quickly does the charge circulate? Like how quickly does it go around? This is a question we answer. You guys should know how to do this. This is 9A material. So the force is just, this is just centripetal acceleration. It's the mass times the radius times the angular velocity squared, right? This is the centripetal acceleration. This is just the mass. So this is just Newton's second law. And so we know the magnitude of the force. It's Q times V times B. And because they're perpendicular, there's no sine theta. I'm actually going to drop the magnitude of Q because we're assuming it's positive. And so this has to be equal to m r omega squared. No, it's v squared over r, or omega r, or r omega squared. Yeah, I did demonstrate how I got the clockwise using right-hand rule. So the magnetic field, or v points to the left, or to the left, magnetic field points in. So the force is up. And so that's when it's at the bottom. And so that will apply a force this way. And then as it loops around, that force will just continue to point towards the center, causing it to turn over and over again. Right, okay, so now just a quick reminder from 9a. Velocity is equal to r omega. And so we can just substitute. We get that Q times B times r omega is equal to m r omega squared. Or solving, we get that omega, which is the angular frequency. Why should it be going counterclockwise? The force is, if it's going to the left, and the magnetic field is into the page. Yeah, oh, yeah, no, that's right. I should have drawn it. Wait a minute, hold on. Let me make sure that I'm doing this right. Yeah, it should 100% be going counterclockwise. No, you guys are right. It's just for me to see, because I'm watching myself do it with the left hand, so I do it with the left hand. But anyway, yeah. So yeah. I just need to make sure that I do it the appropriate, I need to make sure that I do it with my hand the correct way first, and then I can draw it using the appropriate tools. So there we go. Oh boy. Oh boy, where'd it go? There we go. Right-hand rules on non-mirrored things are annoying. Okay, so I was using my left hand. So I'm going to use, so if you guys take your right hand, okay, this is why it was confusing. Okay, so if the velocity, so I was doing it the reverse way, but that's out of the screen for you, whereas the magnetic field should point into the screen. That's why I was confused. Okay, so let's assume that it's going to the right. So it's either at the top or the bottom of the loop, it's going to the right. So I'm going to curl my hand into the direction of the magnetic field, which for you guys should be into the screen. So that's why it's towards me. It's out of the, like it's actually pointing towards me, which looks out of the screen to me, but for you guys, it's into the screen, right? So velocity this way, magnetic field this way. So the force would be up when it's at the bottom. So that means that it would start to circulate to the left. When it's on the right-hand side, the force is up, magnetic field is into the screen still. So the force is to the left. So so the acceleration will be to the left. And so it'll go in a circle counterclockwise. Yeah, sorry about that. It's just, I just have to keep in mind that I'm doing the opposite of whatever for you guys. Right, maybe I'll mirror my video next time. Right, but anyway, so after going through all of that calculation, we can solve for the angular frequency. So it's just Q times B over M. So this is just to say that the rate at which it goes around the circle, i.e. how many times it does one full circulation per second. No, shouldn't be. So they didn't actually talk about the charge there. So note that it says, is the charge in the figure above positive or negative? So the charge in the figure is negative. I'm using a positive charge because it just makes more sense, or it's a little bit more intuitive. Let's put a plus Q. Right. So the point is it will. So the only thing that affects how many times it goes in a circle per second is the strength of the magnetic field and the ratio of the charge to the mass. It's an interesting feature that it's the ratio of the charge to the mass. All right, so then one more thing to talk about. So we know that if the motion is initially perpendicular to the magnetic field, it'll just move in a circle, depending on what the sign of the charge is and what direction it's moving in. However, if velocity is not perpendicular to the magnetic field, like maybe it has some component that is perpendicular to the magnetic field and another component that's not, then the parallel component of the velocity, the part that's parallel to the magnetic field, plays the role of a spectator. And the perpendicular component undergoes circular motion. So this is to say, if, for example, in this picture, the velocity was not actually just to the right, it was, say, just to the right and also into the board. In that case, the part of the velocity that was into the board would just stay the same forever, because that component is completely unaffected by the magnetic field. The force in that direction from that component, or the force as a result from that component of the velocity, is zero, because it's in the same direction, right, as the magnetic field. So what happens is that the object will continue downwards with whatever speed it was continuing downwards, but it'll circulate as it goes down. And so this type of motion is called helical motion. It just spirals downwards. But if you looked at it from above, it would just look circular. If you looked at it from the side, it would look like, you know, that look like this as it goes down. Right. So I should probably outline that. This is called helical motion. Right. Okay. So that's what happens if you just stick a charge and make it move in a magnetic field. It'll typically, as long as the magnetic field is constant, it will undergo circular motion of some kind. Whether it's helical or not is a different story, but it will undergo some sort of circular motion. But we started off talking about the force between two wires, or in particular, the force on a wire from a magnetic field. So let's get back to that. Because we still want to be able to explain why the wires seem to have a force between them when there's current in them. So we're going to try to answer the question. We don't yet understand how to actually create a magnetic field from current in a wire. We're just going to assume there is some magnetic field and ask what is the force on a current carrying wire. So for the beginning, we're going to assume that it's constant. Or let me rephrase. For a lot of what we're talking about today, we're going to assume the magnetic field's constant until the very end. But as long as you work infinitesimally, a lot of this stuff will still work for non-constant magnetic fields. Right. So let's consider a curvy wire. So I'm going to do my best to draw. So we have our magnetic field, which is just constant. And remember, a constant field just means the field lines are straight and equidistant from each other. And then we have some wire, like that. It's just some piece of wire. Maybe it's connected on one end to something and another end to the other thing. And so this wire has some current through it, say I, that you just like attach it to a battery or something like that. So it has some current through it. And so we're interested in what the force from the magnetic field is on the wire. So what we're going to do is, rather than just try to handle the wire in its entirety, because it's curvy, different parts of the wire will feel different amounts of force, because the charges in the part of the wire that are going here are going in a different direction than the charges in the wire that are here, right? So they'll feel a different amount of force because their charge is moving in the wire. So let's just look at, say, this chunk of wire over here. Let's call that length of wire, it has a direction, which points in the direction of that chunk of wire, and we'll make it so that it points in the direction of current as well, and it has a length infinitesimally. So let's call that chunk of wire the vector dl. So let's think back to when we first started talking about current. The definition of current is that current is just rate of change of charge across a particular it is the rate at which charge crosses a particular checkpoint. Written another way, it is the time derivative of current. Sorry, time derivative of charge. And so we can actually just use the chain rule here in a kind of dirty way to figure out how this relates to dl. So here we can write that the derivative of q with respect to t is really the derivative of q with respect to the length, or the path length L, times dl dt. And this dl dt, this is really the speed of the charge in that wire, or in that segment, dl. That dl dt is just the rate at which those charges are moving in that segment. And so this can be written as dq dl times v. Or, rearranging, we get that I times dl is equal to dq times v. And maybe we can see where we're going, because now we have a charge times a velocity. And so maybe we can now figure out what the magnetic field is. So just as an aside, recall that at least for simple currents, not ones that have non-constant current density, for simple currents, the the current flows in the direction of the wire. That's kind of a sensible thing to say, which implies that the velocity vector of the charges is parallel to the path length vector dl. And so the end result then is that we can write a vector equation. IDL vector is equal to dq times v, the vector. And so now we can actually figure out what the force is on that small chunk of charge that's moving in that bit of the wire. The charge in segment DL, well, it's dF, because it's a small amount of force, is dq times v cross b, because that's the amount of charge is dq, the amount of, and the speed is v. And so we can substitute. We have that the force on that small chunk of wire is actually I times dl cross b. So that is the force on a small chunk of wire. It relates to the current and the direction that that current is going in. So I dl is basically a current vector that's infinitesimal. Think of dl as just an infinitesimal vector that points in the direction of the wire, and you're good. So we can then, if we need to, for some complicated wire, all we have to do if we want to find the net force on the wire is just add up all of the forces from all the little segments. But in the simplest case, where we have a straight wire perpendicular to the magnetic field, the integral just becomes relatively straightforward because there's nothing changing, so we can just do the integral. We get that the force on a small chunk of that straight wire, so like the picture here is something like this. You have a magnetic field, and then you just have a straight wire that has current running, say, up it or something. So this is a lot simpler of a case. We would have that the force is just the current times the magnetic field. These are all magnitudes now, being magnitude of the magnetic field, times the length dl, times the vector L hat cross B hat. So just to be clear, when I'm saying L hat, that's just the vector that points in the direction along the wire, in the direction of current flow. And B hat is just the unit vector that points in the direction of the magnetic field. So this is just to say, this is like that cross product is just a vector perpendicular to both. And it has a unit length, so it doesn't affect anything. This is just a way to get the correct vector because it's a cross product. So in this case, what we find is that the wire, the force on the wire can just be directly integrated because this thing's a constant, it's 1, and then you can just integrate dl along the whole length. So this is just an integral from 0 to L of I times B times dl, which is just IBL. So if you have a long straight wire that's perpendicular to a magnetic field, and you have current running through it with magnitude or with value I, and then you just multiply them all together and you get the force on the wire. Now, unfortunately, this isn't the most useful result because in reality, the wires that have current running through them typically have to loop back around somehow, right? If only because that current has to come from somewhere and it has to go somewhere. So the second most simple example, and it really is quite simple, nearly as simple as the straight wire, is the simple square loop. So we're going to talk about torque on a loop. And the reason we're going to talk about torque is because we're going to find that the force actually, the net force on the loop vanishes. We're going to use the just so for any length of wire with current flowing through it, I, and length L, the magnitude of the force on that length of wire is I times B times L. So let's imagine that we have a magnetic field this time pointing straight down. We'll get to motors at the very end of lecture today. Magnetic field points straight down. It's constant. And let's say that we have a loop of wire, a square loop of wire, like this. Let me make this better. Sides are supposed to be perpendicular because it's supposed to be rectangular. Let's say that this distance here is Z, This distance here is y. And let's say that there's current running through it this way. Just running counterclockwise. So now we can just start thinking about what is there, like what's going on in the systems. Let's do a quick analysis. So first, the force on the left and right sides are 0. And the reason for that should be fairly clear. In that case, the wire, which is just made up of a vertical chunk, points either parallel or anti-parallel to the magnetic field. And so that produces 0 force. We have to have that the wire is perpendicular to the magnetic field. And so the way we're going to treat this is we're just going to treat this like 4 separate wires, each with current I flowing through them. And then we'll add up the forces and add up the torques and so on. And you can do that because things can be superimposed. So there's no force on the left or the right segments of the square. Another thing to note is that the force on the top and bottom segments have the same magnitude. They have the same length, they're in the same magnetic field, and they have the same current running through them. And so the force on each of those segments is just I times B times Y. The length of the top and bottom segments are Y, the current running through it is I, the magnetic field is B. Now, the next question is, what direction do the forces point? So the force, so we can use the right-hand rule to show that the force on the top points in the opposite direction as the force on the bottom. Now let me explain that in a minute, or now I guess. So we can use the right-hand rule. So remember, the force is just the direction of the current. That's effectively what these two things are together. I times L hat is just a vector with magnitude equal to the magnitude of the current. Direction is the direction of current. So let's do this. So we have, if you guys aren't doing this, like shoving your arm all over the place during exams, I don't know what you're doing. Right, so let's look at the top. So we have the current, or the path length, the path vector for the top wire points in the same direction as the current. So that's to the left. The magnetic field points downwards. So the force points out of the screen for you. So the force here looks like this. Now, what about for the bottom? Well, here we have the path length vector points to the right, because that's the direction the current's going. Magnetic field points down. And so the force points into the screen for you. And so what we find is that even though they have the same magnitude, they have opposite directions. So the net force, F net on this square of wire is 0. There is no net force, it'll stay in place. Now that doesn't mean that it won't move, because torque can also cause motion. It just doesn't move the center of mass. So often when the force on something is 0, it's useful to then ask, what about the torque? Because the torque can be non-zero even if the force is 0. So let's ask about that. Let's try to think about that a little bit. So the torque on the system is a little bit harder. So I'm going to try to draw this viewed from the side. I'm trying to draw this like in 3D-ish. So this is viewed from the left side. Let me do this a little better. So the current goes this way. So the top is over here. Oh no, it's not erasing. There we go. Top is over here. The bottom is over here. And when I say top and bottom, that's referring to the same top and bottom that we had in the first picture. And so now in this picture, we have the magnetic field points to the right. Let me put that in purple. And it passes through the whole thing, but I'm not going to draw it passing through there. Okay, so let's now figure out what direction the forces are. So we've already established that that on the top, it should point up or out of the page. In this picture, that corresponds to up in this picture. So we have the force of the magnetic field here points up, and the force on the magnetic field here points down. So just imagine that I'm putting my eye like here. And I'm looking at it from the side. That's all. So intuitively, you guys probably have this notion that this thing will rotate, right? It'll rotate about maybe this central axis because it experiences a downward force on one side and an upward force on the other, so it'll start to spin. And so the torque about the center of the square, which I put a little point there, that's not zero. So let's ask the question, what is the torque? So the torque, the formula for torque is the moment arm crossed with the force vector, right? So here, R points from the center of the square. So we're computing torque about the center of mass, by the way, to the center of the line segment. So that implies that the magnitude of our moment vector is just, well, looking at our picture, that would be this vector, right? And so that has length z over 2. Further, we know from this picture that that vector r is perpendicular to the force vector. Just by looking at the picture, you can tell that. And so what that implies is that the magnitude of the torque is equal to the product of their magnitudes. So what we find is that the magnitudes of the torque on the top is equal to the magnitude of the torque on the bottom, which is just z over 2. That's the length of the moment vector. And then we just multiply by the force, I times b times y. Finally, you can use the right-hand rule again. So the vector is this vector, say for the bottom, so it points to the right and then down. So that would point into the page. And then you could do the same for the left. It points to the left and up, so also into the page. They point in the same direction. They're parallel to each other, and they have the same magnitude. So that implies that the net torque on the system is just, or the magnitude of the net torque is just the sum of the magnitudes of the torque on each side. And so that's just, well, they both have z over 2 times I times b times y, or rewriting it, it's I times y times z times b. And I wrote this in a very particular way because y times z is a special thing. So, but I'm just gonna put a square around this really quick. So that is the net torque on a square loop or rectangular loop in a constant magnetic field. Now, note that that's only the torque when it's still flat. Once it starts to rotate, the torque is going to change, right? Because that angle changes, but we'll see what happens. So here's where we introduce this notion of the magnetic dipole moment. It's a nice segue. So in this loop of wire, we can generalize that idea because this here, this is the area of the loop. And so if we had just replaced, if we had just put in this formula, IAB, then we would get that that's just the correct torque on the loop. Now, we're not quite there because the area doesn't change, but the torque does as the angle does. So we have to fix it a little bit. Now, before we proceed, I just want to add one more thing in. If we had had a bunch of these loops stacked on top of each other, so like a big coil that's really like thin, but it has a whole bunch of loops with current passing through it, each single one of those coils would have felt the same torque. So the whole system would have felt the torque from all of those coils. So when we deal with coils, in a coil of wire, the torque is effectively multiplied by the number of loops in the coil. And we typically call that capital N. So you might have a loop of wire that has 10 coils, and so whatever the torque would be from one coil, you just multiply it by 10, and that will be the total torque. And so what we can do is we can actually combine the characteristics of these loops of wire into a single number, just like how we combined the characteristics of a positive and negative charge producing a dipole, like we needed to talk about how much charge they have and how far away they are from each other. That gave us a single number. In fact, it gave us a vector, but it gave us a single magnitude that told us how strong the torque was on it, on the electric dipole in an electric field. Here, we can combine the properties of the system, not the external magnetic field, but the properties of the system, to give us another number that will characterize the torque on the system in a magnetic field. So the properties of the system here are things like the area of the loop, the number of coils of the loop, how much current is in the loop. And so you can check if you have twice as many coils, you'd have twice as much torque. That we just went over that. If you have twice as much current, you would also have twice as much torque. And if the area was twice as large, you'd have twice as much torque. Again, putting all of those things together, what we can do is we can combine them into the magnetic dipole moment of the loop. Just like how we did for the electric dipole moment, we multiplied the distance times the charge. And so the magnetic dipole moment, given the Greek letter mu, it's not a u, it's a mu. This is equal to, or at least the magnitude of this thing, because this will be a vector too, is equal to the number of coils times the current times the area. It's Nia. It's the current in the wire. And A is the area of the loops. I'm gonna put a box around this. This is super useful. So you can see that in this simple example, N is 1, there's only one loop of wire. The area is Y times Z, and the current is I. So you could probably guess that the torque is just something like the magnetic dipole moment times the magnetic field. Not quite that straightforward, because the coil can turn, right? In this case, it's a loop. It can, once it experiences torque, it'll start to rotate. So the question is what happens? So once a coil starts to turn, we expect the torque to reduce. And the reason that's not so surprising is because the torque should be 0 when it's perfectly aligned, right? Because then then there's no forces and no torques, or all of the torques will cancel out. And so we can kind of show this geometrically too. So here's our magnetic field. I'm going to draw a side view of our current carrying loop. Why can't I draw a straight line? There we go. So here's one end. So we have current coming in over here. Sorry, current coming out over here and current coming in over here. So this is, again, the same side view that I did before, just more extreme. We have current coming on the side closest to us. It's going to the right. And so the force on the bottom right, remember, this is the same diagram. So this is the bottom, this is the top, and then this is the left, right? That's the picture here. So the force on the bottom bit, the current is running into the screen, The force, or the magnetic field, is to the right, so the force is still down. And similarly, on the top, the force is still up. But now the torque, which is R cross F, is smaller because they're not at right angles anymore. And the torque is maximized when the moment vector is perpendicular to the current. And so what we find is that if we have a vector that pointed this way, so that this angle is theta, well, when that angle is 90 degrees, the torque is maximized. But in this case, this is not 90 degrees anymore once it started rotating. Once it has started rotating, right? So in this case, we can do the same calculation, but with this new angle of the loop, and we would find that the torque on the top, the magnitude, is the same as the magnitude of the torque on the bottom, but now those magnitudes are different. They are equal to the magnitude of the force times the length of the moment arm times the sine of theta, which would just be IAB sine theta. This here being the moment arm. And so if we define the vector A so that it points out from the coil, using the right-hand rule to define the direction, right-hand rule of the current. So that would mean, in this case, you would curl your hand in the direction of the current and your thumb points in the direction of A. So in this picture, I curl my hand in the direction of current, so A would point out of the screen, right? So if we define A that way, and it has magnitude equal to the area, and define the vector, which is Ni times the vector A, then we find that the torque on the dipole as a vector is the cross product of the magnetic dipole moment and the magnetic field. So this is good for us. This buys us a lot, because now you can use so all you need to know is the direction the area points, or the coil points in, which is encapsulated by the area vector, and then the number of coils in the current, and you can use that to find the torque on any coil. This doesn't just apply for square coils. This holds generally for any planar coil. In a constant magnetic field B. Now, a planar coil is just a coil that you can fit on a piece of paper. It means that you can lay it flat. Like if you had a coil that was like this, but then bumpy, then this formula doesn't apply. But this does apply for any planar coil, for any coil that you can just like lie down. And obviously the approximation will get worse the more bumpy your coil is, or the less planar your coil is, because as long as it's only a little bumpy, it's still a decent approximation. So just as a reminder, the torque on an electric dipole is, in an electric field, is P, the electric dipole moment, across the electric field. So there's like a clear analogy here. It seems like if you do everything in the electric case and then just replace P with mu and E with B, then you'll get the same equivalent or the same analogous things for the magnetic field. So just as a quick point of, or a quick example for you guys, you can check out a calculation in the textbook. It's example 4.2.1, where basically in the textbook, you're just calculating the torque on a loop of current. So you have some loop with current flowing in it, and it's asking you to calculate the torque on it. just a good way to get practice with these sorts of things. So the next question is, I said that it works for any planar coil, but we only actually did this for a square coil where the area is nice and well defined and where the force is only on one side and it's constant on that side and so on. So how does it actually, like, I need to give, maybe you guys don't care, but I feel like I have to give some sort of justification that it does indeed work for non-square or non-rectangular coils. So let's do an example for a circular loop in a constant B field. So we're going to do the circle and it will be a little bit involved. So put your pants on and let's do this. So here's the picture. We have a magnetic field, has to be constant. We're gonna have some current. Oop. Yeah, you guys should be wearing pants. I have to wear pants. Because if I stand up and I'm not wearing pants, I would get in a lot of trouble. Well, if current going counterclockwise, that's a leg with pants on. Yes, I do have to wear pants. Well, it has some current going through it. And what we're going to ask is we're going to try to find the torque on this circular loop. So let's just put there's a radius r here. Let's put a coordinate system, standard coordinate system at the origin, so x and y, and then we'll have z pointing this way. You can see both my arms. By the way, the coordinate system we choose has to be right-handed, which means that if you cross the y, if you cross the x coordinate axis with the y coordinate axis, it should point in the same direction as the z coordinate axis. Hence why z points out of the paper in this case. So what we're going to do is we're going to basically use a combination of polar coordinates to characterize the positions in the circle, as well as Cartesian vectors to find, so then we can do cross products, to find the torque on an infinitesimal length of that wire, just like we talked about initially when we were first talking about forces on a wire. So we know how to find the force on an infinitesimal chunk of wire. Where is it? Now we just need to find the torque, and that will be relatively easy once we do it, but it takes a little bit of setup. So let's just pick a random chunk. Say this chunk here of wire has some current run through it. I will characterize its position as an angle theta, or sorry, phi. And now we just want to ask, what is the torque on that chunk of wire? And then we're going to add them all up. And I'm saying that the magnetic field points in the x direction and it's constant, so it's just B. The magnitude's just B. Right, so in order to find the force on that chunk of wire, what do we need? We need dl. We know how much current there is, but we need to know what dl is for that chunk of wire. Now dl is the infinitesimal length of infinitesimal vector that points in the direction of the path, and it has length equal to the length of the infinitesimal vector. And we're going to use a mix of Cartesian and polar coordinates here so that we can make it sensible. So we're going to write the vector in terms of I, j, and k, but we're going to parameterize that vector, so like the length and things like that, in terms of the polar coordinates. So we need dl of phi. So we need the length vector, the path length vector at that angle phi. So let's zoom in a bit. So here's a segment of our, I'm trying to zoom in, but it's kind of hard to make it look good. Right. So here's our segment of our circle. Let's say that zoomed in a lot. So here's the angle phi. We want to find the length of this vector and the direction of that vector. So that vector spans an angle d phi. It's an infinitesimal angle, so it'll have length dl. This length here is r. So automatically, just by using the arc length formula, we know that dl, the length, is equal to just r times d theta, sorry, r times d phi. Okay, what about the direction? Now for the direction, we have to do a little bit of geometry. It's a little bit involved. we're going to want to write it in terms of I, j, and k, where I points to the right and j points up. So let's zoom in on that vector. So we have our vector here. It's our vector with length dl. It's separated from the origin by some distance r, but this angle here is phi. And so this angle here is phi. And so if we complete this triangle, this angle is phi. It's just a little bit of geometry, but think about it. If you're a little bit stuck, just think about it a little bit and you'll come to it. And so then we can find the components of that vector. It's to the left and up, and that's just using standard trig with cosines and sines. So dl is the vector r times d phi, and then it's negative sine phi in the I hat direction, and it's plus cosine phi in the j hat direction. Okay. So on a small segment, or on this segment of wire, the segment of the loop, the force then can be written as I times dl cross b. And we know what b is. It's just b in the I hat direction. We know what dl is now, so we can just do this product, or do this cross product. So it's I times r d phi, and then we have to do a cross product of minus sine phi in the I hat direction plus cosine phi in the j hat direction, cross b in the I hat direction. So this is just minus IRB, cosine of phi, d phi in the k hat direction. So remember, I cross I is 0, j cross I is negative. It's negative k. So that's the force on that small chunk. So we can't just add up the force everywhere, because the force everywhere will be 0. We need to find the torque of that chunk and then add all of those up. So the torque is a little bit more involved. Well, not really. We just want to find the torque from the center. We know the distance that it is from the center, it's r, and we know that that center, because it's a circle, we know that that cross product is just a product. Actually, no, sorry. R is perpendicular to dl, but it's not necessarily perpendicular to dx, so we have to be careful here. So we want to compute the torque. So it would be d tau, this is at a position phi, is just, well, what's the vector that points from the origin to the place of interest? Well, that vector has length r and has cosine in the I hat direction and sine in the j hat direction of phi. So this is r times cosine phi I hat plus sine phi j hat. And we have to cross that with, I'm going to put a negative sign out here. I'm actually going to move all of the constants out to the side. So it's minus I r squared b cosine phi I hat plus sine phi j hat cross cosine phi k hat in the, or times the infinitesimal d phi. Again, this is just a cross product we can do, but it's a little bit messy. It works out that you get I r squared b times cosine squared phi j hat minus cosine phi sine phi I hat, again multiplied by the infinitesimal d phi. And so that's the torque on that tiny segment. Now we just have to do an integral. So we integrate from 0 to pi. Because we have to, or sorry, 0 to 2 pi, we have to add up the contribution from every single angle. So the net torque is an integral from 0 to 2 pi of I r squared b cosine squared phi j hat minus cosine phi sine phi I hat d phi. Now that's an integral that you can in principle do. For the second term is relatively easy. It boils down to basically sine squared. First term is a little bit less easy because you have to use a double angle formula, but using that cosine squared is 1/2 cosine of 2x plus 1. But it's doable, and I trust you guys to be able to do integrals. And so the end result is you get I r squared b times pi in the j hat direction minus 0 in the I hat direction, which is just I times pi r squared times b in the j hat direction. And voila, that's the area. So we can compare. Let's check that the vectors point in the same direction too. So compare with torque is mu cross b. So in this case, mu is I times the area, pi r squared. And there's one loop, so times 1. And what direction is it in? Well, so we use the right-hand rule. So the current circulates to the counterclockwise direction. So the vector A points out of the screen, which is in the k hat direction. So this is k hat. So the torque, which is mu cross b, is just I times pi r squared times b times k cross j. Now, sorry, k cross I, because b points in the I direction. Now k cross I is just j, so this points in the j hat direction. And you can check that these two things agree. And so hopefully at least that's good evidence that this method works, that you can just use the magnetic moment, magnetic dipole moment, rather than going through this kind of annoying process of integrating the whole thing, because you don't need to. As long as it's a planar coil, you don't need to. We're not going to get through as far as I wanted to, but I will do as much as I can. Right, so this is all just to say that the similarities between the dipole, the electric dipole, and the magnetic dipole are pretty general. Like, it's not just for square loops of current that you get this relationship that the torque is the dipole across the field. It's for basically any loop of current. And so that relationship that you can just replace the electric dipole with the magnetic dipole and the electric field with magnetic field, you can use that to get results that would otherwise be kind of involved. So let's just get one. Remember, P is the electric dipole moment. So if we make the replacement that P goes to mu and E goes to B, well, everything should track, because all of the results that we derived for the electric dipole just relied on the fact that the cross product gave you the torque. We derived the potential from that. We talked about the force, which comes from that. So as long as the torques have the same form, you should be able to derive the potential energy as well. And so we can get the potential energy from that relationship. And you can go through and double check that everything tracks. You can just use the exact same methods that we use to derive the potential energy for an electric dipole to find the potential energy for a magnetic dipole. So the electric dipole potential energy is minus P dot E. So using the analogy, we find that the magnetic dipole potential energy is minus mu dot B. And again, like I said, you can go and double check this, and everything tracks. It works precisely. So there's a good example where you can use energy conservation by noting the fact that the potential energy plus kinetic energy is conserved to solve for current in some cases. Like if you know what the initial potential and kinetic energies are, and you know what the, if you don't know what the initial potential energy is, but you know what the kinetic energy is, and then you know what happens, you can actually back solve to find what the current in a loop is. Amanda, to find the direction that the loop rotates, we would note that the torque points in the plus j direction. So if the torque points in the plus j direction, that means that it will rotate like this way. It'll spin. So the next question that you might have, actually, we are just about done. So we didn't get a chance to talk about motors. So there's a little bit that I want to talk about what happens if you put a magnetic dipole in a non-uniform field. I suggest that you guys go take a look at that for lecture on Monday. I'm going to end the lecture here, and I'm just going to fly through that on Monday so we can get to DC motors on Monday. Sorry, not Monday, on Tuesday. Because DC motors are kind of, it's an actually useful application of something that we've talked about in this course. So I do want to get a chance to talk about it. So go take a look at the end of section 4.2. That's where the end of the lecture notes are based off of. We're going to talk about dipoles in a non-uniform field and DC motors. Right, so I'm going to end lecture here. And